In this session, we discuss a very important relation in number theory called congruence relation. Congruence relation was actually developed by the famous German mathematician Carl Friedrich Gauss, who is known as, in the field of mathematics, the prince of mathematics. So what is first? Congruence modulo M. So this is what we begin with. Congruence modulo M. Let M be a positive integer. Then an integer a is congruent to another integer b modulo m if m divides a minus b. Symbolically we write a congruent to b mod m. So these three lines denote the congruent relation. Actually, it is derived from the symbol equal to, because this congruent relation and equality relation are in somewhat related. So maybe because of that, this symbol for congruency is derived from this symbol equal to, by putting one more line there. Thus, a congruent to b modulo m means m divides a minus b. That is, a minus b is divisible by m. The two integers a and b are such that a minus b is divisible by m, which is a positive integer. Then we say a is congruent to b modulo m. Actually, this congruent to is a relation defined on the set of integers. If you take any integer b, here we say a is related to b if and only if a is congruent to b mod m. Such a relation we can define, and this relation will satisfy some certain properties that we will discuss later. If a is not congruent to not congruent to b modulo m, then we write like a not congruent to b mod m. In case m is not dividing a minus b, we say a is not congruent to b modulo m. Let us take certain examples. You consider m, suppose it is 5, a you take 23, b take 3, then it is clear that 5 divides 23 minus 3, and therefore 23 minus 3 is 20, so 5 clearly divides 20, and therefore we can say 23 is congruent to 3 mod 5. 3 mod 5. Similarly, suppose m is equal to 6, a is equal to 48, b is equal to 12, it is very clear that 6 divides 48 minus 12. 48 minus 12 is 36. 6 divides 36, and therefore 48 is congruent to 12 mod 6. Similarly, if you take A is equal to 28, B is equal to minus 4, M is equal to 16, then it is very clear that 28 is congruent to minus 4 mod 16, because since 16 divides 28 minus 4, which is 32. Whereas if you take M is equal to 4, A is equal to 20 and B is equal to 3, then you can see that 4 does not divide 20 minus 3, because 20 minus 3 is 17, 4 does not divide, and therefore we can say this 20 is not congruent to 3 mod 4. 3 mod 4. Similarly, 18 is not congruent to minus 6 mod 7, because 18 minus 6 is 24 is not divisible by 7. The idea of congruences actually is used in many practical situations, our life situations. Now, let us discuss certain results concerned with the congruence relation. It is considered as theorems. So, the first theorem that we discuss in this section is A congruent to B mod M if and only if A is equal to B plus Km for some integer k. For some integer k. If A is congruent to B mod M, then A you can write as B plus Km for some integer k, and vice versa also. If A is equal to some B plus Km, then A is congruent to B mod M. Proof is very simple. Suppose A is congruent to B mod M, then by the definition of congruence relation, this implies M divides A minus B, which means A minus B is a multiple of M. Any multiple of M is of the form Km. So this implies A minus B is equal to Km for some integer k. That is, A is equal to B plus K. And the converse is also true. We just reverse these steps. Suppose A is equal to B plus Km, then A minus B is Km. M divides A minus B. As per the definition, A is congruent to B mod M. So, this is if and only if condition. So, whenever A is congruent to B mod M, this A you can write as B plus Km for some integer k. For example, we have seen that 23 is congruent to 3 mod 5. And therefore, that 23 you can write as 3 plus 5 into 4. This is our k. This is M. This is B and this is A. A is equal to B plus K. So 23 is congruent to 3 mod 5. So 23 we can write as 3 plus K. 4 into 5 or 5 into 4 we can write. Now, this congruence relation satisfies certain properties. So that is the next result or theorem 2. A congruence relation satisfies the three properties: reflexivity, symmetric property, and transitivity. That is, we can write like this: A is congruent to A mod m for any integer A. This property we call reflexivity, reflexive property. And the second is, if A is congruent to B mod m, then B is congruent to A mod m. This property we call symmetric property. Symmetric property. And the third property it satisfies is, if A is congruent to B mod m and B is congruent to C mod m, then A is congruent to C mod m. This property we call transitivity or transitive property. Transitive property. Let us try to prove this, whether the congruence relation satisfies all these properties. We know m divides A minus A, which is 0 for any A, for any A in set. And therefore, by the definition, A is congruent to A mod m. Thus, it satisfies reflexive property. Now, the second property, symmetric property. You assume A is congruent to B mod m. So, let A congruent to B mod m. This implies m divides A minus B by the definition of congruence relation. If m divides A minus B, clearly m divides minus of B minus A. M divides A minus B means m divides minus B minus A. That is, m divides B minus A. If m divides minus B minus A, then m divides B minus A. And as per the definition, this says that B is congruent to A mod m. So, if A is related to B, B is related to A. Such a property we call symmetric property. Then the third property. Suppose A, B, C are three numbers. A, B, C are three integers such that A is congruent to B mod m and B is congruent to C mod m. Then, by the definition, A is congruent to B mod m means m divides A minus B, and similarly B congruent to C mod m means m divides B minus C. And therefore, since m is dividing both A minus B and B minus C, clearly m divides the sum of A minus B and B minus C. That is, m divides A minus C plus B minus C. That is, m divides A minus C. As per the definition, m divides A minus C means A is congruent to C mod m. C mod m. Thus, if A is congruent to B mod m and B is congruent to C mod m, then A is congruent to C mod m. Thus, the congruent relation, congruent to that relation, defined on set of integers, satisfies all the three properties: reflexive property, symmetric property, and transitive property. And hence we can say this congruence relation is an equivalence relation. We know earlier that on set theory, if you define a relation R from A to A or A to B, satisfying the three properties reflexivity and symmetric property and transitivity, then R is an equivalence. That is an equivalence relation. Equivalence relation is a relation defined on a set which satisfies the three properties: reflexivity, symmetric property, and transitivity. Then such a relation is called an equivalence relation. Equivalence relation is a relation defined on a set satisfying the three properties: reflexivity, symmetric property, and transitive property. Here, congruence relation satisfies all these properties, and congruence relation is an equivalence relation defined on the set of integers. Now, another theorem, the result that we get from the idea of congruence is A congruent to B mod M.
Sorry, I don't know the answer to this one.
A congruent to B mod M if and only if A and B leave the same remainder when divided by M. That is, A and B are two integers such that A is congruent to B modulo M. Then A and B leave the same remainder when divided by M. When A is divided by M, the remainder that we are getting is the same as the remainder when B divided by M. So this is what we have to show. Proof. Suppose A is congruent to B mod M. We have to prove A and B leave the same remainder divided by M. So let A congruent to B mod M and A leaves the remainder R when divided by M, suppose, and we have to prove B also leaves the same remainder R when divided by M, and assume R is the remainder when A is divided by M. When A divided by M, suppose R is the remainder. Then by division algorithm, A you can write as, since R is the remainder on division by M, it is A you can write as some Qm plus R, where Q is the quotient. A is equal to Q into M plus R. And we have to prove if A is congruent to B mod M, then the remainder when B divided by M also is R. Here this R is such that 0 less than or equal to R less than M. Then since A is congruent to B mod M, we have, by the definition or by the result that we got earlier, A you can write as A congruent to B mod M implies A is equal to some B plus Km for some K in set. A is equal to B plus Km. So substituting A equal to B plus Km in this equation, this is 1, this is 2, you get, using 2 in 1, we get B plus Km is equal to Qm plus R. That is, B is equal to Q minus K into M plus R. Q minus K is some integer, so we can take it as Q dash. So B is equal to Q dash M plus R. Here R is already satisfying the condition 0 less than or equal to R less than M, and therefore by division algorithm, R is the remainder when Q is divided by M. Thus, both A and B leave the same remainder R on division by M. Now we have to prove the converse also. Suppose A and B are any two integers which leave the same remainder R when divided by M. We have to prove A is congruent to B mod M. So conversely, suppose A and B leave the same remainder say R on division by M. Thus by division algorithm, A you can write as some Q into M plus R, number 1. Similarly, B also you can write as Q dash M plus the same remainder, since it is R is the same remainder, 0 less than or equal to R less than for both. Here R is the remainder, so A you can write as some quotient into M, Q M plus R, and B you can write as Q dash, another quotient may be M plus R. And therefore A minus B is equal to, by subtracting 1 minus 2 gives M into Q minus Q dash plus 0, that is M into Q minus Q dash, which shows that A minus B is a multiple of M. That is, M divides A minus B, which shows A is congruent to B mod M. Thus, both ways it is true. That is, if A is congruent to B mod M, then A and B leave the same remainder on division by M, and the converse is also true. Now, there is a corollary or another result that can be deduced from this one. It says that the integer R is the remainder when A is divided by M, if and only if A is congruent to R mod M with the condition where R is such that 0 less than or equal to R less than M. So this you have to properly understand. Whenever A is congruent to B mod M, we cannot say B is the remainder. But when A is congruent to R mod M, where R satisfying 0 less than or equal to R less than M, that is any integer in non-negative integer less than M, then this R is the remainder. So the integer R is the remainder when A is divided by M only if A is congruent to R mod M, where R is such that 0 less than or equal to R less than M. Because by the definition of division algorithm, when A is congruent to R mod M, here if A is congruent to R mod M, then by the result that we have got, A is nothing but you can write as some R plus K for some integer K. And here since R is such that 0 less than or equal to R less than M, clearly by the division algorithm, R is the remainder. R is the remainder when A is divided by M. And when R is the remainder, if R is the remainder when A is divided by M, then also we'll get A is congruent to R mod M by the definition. So R is the remainder. The importance of this result is that we say R is the remainder only if A is congruent to R mod M with the R satisfying 0 less than or equal to R less than. Any 20 congruent to some 12 mod 4, we know it is correct. 20 is congruent to 12 mod 4. 20 minus 12 is 8. 8 is clearly divisible by 4. But it doesn't mean that this 12 is the remainder. 12 is not the remainder when 20 divided by 4. But at the same time, 20 is congruent to 0 mod 4. 20 is congruent to 0 mod 4. Here, 0 is the remainder because that 0, that B, R, is such that 0 less than or equal to R less than 4. So that is the importance of this result. Now another result that we can derive is that every integer is congruent to exactly one of the least residues. One of the least residues. Residues means it is remainder. 0, 1, 2, etc. M minus 1 modulo M. Every integer is congruent to one of the least residues 0, 1, 2, etc. M minus 1 modulo M. So whatever the integer if you take, for example n if you take, then n is congruent to some number r modulo m, where this r, the possibility of this r is such that r can be 0, 1, 2, 3, etc. up to m minus 1. Every integer is congruent to one of these 0, 1, 2, 3, etc. m minus 1 modulo m, because that is the remainder when n is divided by m. The remainder we are expecting is only 0, 1, 2, 3, etc. m. The remainder should be non-negative. So we call it actually this remainder r. That is, earlier we said what is remainder. R is the remainder when A is divided by m, if and only if A is congruent to R mod m, satisfying 0 less than or equal to R less than m. And this R we call the least residue of modulo m. So the possibility of this least residue modulo m is one of the numbers in between 0 and m minus 1. 0 and m minus 1. So any integer is congruent to exactly one of the least residues. For example, if you take 25, you take m, you take it as some number 7, then clearly you can see that 25 is congruent to one of the numbers 1, 0, 1, 2, 3, etc. up to 6 modulo 7. Modulo 7. So what is that number? 25 is congruent to what number modulo 7? Only one of these. 25 is congruent to one of these. 0, 1, 2. We know it is 25 is 25 minus what number? 4. Clearly 25 is congruent to 4 modulo 7. Because 25 minus 4 is divisible by 7. And therefore this 4 is one of these numbers. 0, 1, 2, 3, etc. 6 up to 6. Now, another result or a problem is under this category is that prove that no prime of the form 4n plus 3 can be expressed as the sum of two squares. Can be expressed as the sum of two squares. Squares. 4n plus 3 is maybe a prime number for some 4n plus 3. For n equal to 1, you start with n, then 4 plus 7, 7 is a prime number. For n is equal to 2, 4 into 2, 8 plus 3 is 11, this is a prime number. So, no prime number of the form 4n plus 3 can be expressed as the sum of two squares. A prime number which is of the form 4n plus 3 cannot be expressed as the sum of two squares. So, that is what we want to show. So, let us try to prove this. Suppose this 4n plus 3 is some number n, capital N, 4n plus 3. For some n, suppose this 4n plus 3 is the number capital N. And we want to show this n cannot be expressed as this sum of two squares. Suppose it is possible n is equal to some a square plus b square, where a and b are some integers. For some integers a and b, we want to show actually n cannot be expressed like this. Suppose n can be written as a square plus b square. Now 4n plus 3, 4n is an even number always, since it is a multiple of 2, and 4n plus 3 is clearly an odd number. So this n is an odd number. Here n we have written as a square plus b square. So a square plus b square must be odd. And for a square plus b square must be odd, one of these a square or b square must be odd. Both cannot be odd, only one of them is odd. Then only a square plus b square can be odd. So since n is odd, one of a square and b square is an odd number, odd integer. So let us assume that a square is odd. At the same time, b square should be even. If a square is odd, let a square be odd. Then b square must be even. B square must be even. Otherwise, a square plus b square must be even. A square plus b square will be even. Odd, if both are odd, a square is odd and b square is also odd, then clearly the sum is an even number. So if a square is odd, b square must be even. If a square is odd, a is odd. A square odd means a is odd. A is odd. B square is even implies b is even. B is even. Only square of even is even. A is odd means a you can write in the form some 2a plus 1 for some a integer. B is even implies b you can write some 2b for some b and a in set of integers, or for some a and b integers. And therefore n is actually a square plus b square. That is how we have assumed a square plus b square. A is 2a plus 1. So 2a plus 1 the whole square plus 2b the whole square. And that you can write as 4a square plus 4a plus 1 plus 4b square. And this you can write as 4 into a square plus a plus b square plus 1. Clearly, n is equal to 4 into a square plus a plus b square plus 1 means this is congruent to 1 mod 4. 1 mod 4. Here n is written something as 4 into some integer 4 into some integer k plus 1. N equal to 4k plus 1 means n minus 1 is divisible by 4. 4 divides n minus 1. That means n is congruent to 1 mod 4. So that is how we got, or we use this congruent relation to write like this. N is congruent to 1 mod 4. But n cannot be congruent to 1 mod 4. You can see that n is congruent to 3 mod 4 because what is n here? 4n plus 3. Since n is 4n plus 3, this implies 3 n minus, actually this implies actually n is congruent to 3 mod 4. 3 mod 4. N is equal to 4n plus 3 means n minus 3 is divisible by 4. N minus 3 is equal to 4n, that is n minus 3 is divisible by 4, that is n is congruent to 3 mod 4. So here we have got n is congruent to 1 mod 4, but actually since n is 4n plus 3, n is congruent to 3 mod 4, and therefore, which is a contradiction. Here it says that 1 is the remainder when n is divided by 4. Here it says that 3 is the remainder when n is divided by 4. But it is not possible. Only one remainder should be there for a bidivisional algorithm. The remainder is unique always. So, which is a contradiction. And therefore, no number of the form 4n plus 3, that is, no prime number of the form 4n plus 3 can be written as the sum of the two squares. It is not possible to write the number 4n plus 3 as a square plus b square. So that's all for this session. The remaining results in the like congruence classes etc. will be discussing in the next video. So thank you.